Welcome to The Explainer. Today, we're diving into some really fascinating research that gives us a completely new way to find weird or anomalous behavior in complex data. It's a method that looks beyond simple one-to-one connections to find patterns that are hiding in the relationships between entire groups.
So, here's our roadmap. First, we'll talk about why traditional network analysis sometimes falls short. Then, we're going to introduce a much more powerful way to see our data. After that, we'll see how to analyze signals on these new structures, meet the anomaly detector itself, and finally, check out how it performed in the real world. All right, let's get into it. You know, a lot of the time when we try to understand the world, we model it as a network, a bunch of dots connected by lines. But it turns out this simple point-to-point view can actually cause us to miss the bigger picture completely. And don't get me wrong, graphs are amazing for showing these one-to-one relationships. A pipe connects one tank to another, right? A hyperlink connects one website to another. Simple. But this view has a huge blind spot. What happens when the really important stuff isn't happening between just 2 points, but among a whole group?
And that right there, that's the core challenge. A regular graph can show you individual currency trades, dollars for euros, euros for yen, but it might completely miss the coordinated group activity, the actual shape of the interaction, that's screaming that something unusual is going on.
Take arbitrage, for example. That's a situation where you can make risk-free money in a three-way trade. Now, that opportunity isn't a property of a single exchange rate. No, it's a property of the entire loop of three. To even see it, we need a totally new kind of mathematical lens. So, the big question is, how do we actually see these group interactions? Well, researchers are turning to a much more powerful mathematical structure, one that can represent not just simple connections, but entire shapes within the data.
You can think of a simplicial complex as a major upgrade to a standard graph. We're not just connecting dots with lines anymore. Now we can explicitly represent a three-way relationship, like that currency loop, as a single object, a filled-in triangle, or what's technically called a two-simplex. And this is a fantastic way to picture it. Instead of just seeing three separate passes, player A to B, B to C, and C back to A, we can now see a single, cohesive team action. A triangle play. We're fundamentally shifting from seeing individual links to seeing collective shapes in our data.
So, what's the big deal here? Well, by upgrading our view from simple graphs to these much richer simplicial complexes, we unlock a whole new level of analysis. We can finally start to investigate the signals and the flows that are happening on these group interactions.
Okay, so now we can see these complex shapes in our data, but seeing them is only half the battle. How do we analyze the signals, like currency flows or web traffic, that are actually living on them? For that, we turn to a really powerful tool from topology.
This quote from the paper is the absolute key. It says that any complex signal can be broken down into its fundamental building blocks. It's almost exactly like how a prism takes a single beam of white light and splits it into a beautiful spectrum of distinct colors.
Now, at first glance, a signal like this one just looks messy, right? It's complicated, there are flows going in all directions. But this is our white light before it hits the prism. And the Hodge decomposition gives us that mathematical prism to untangle it and see what it's really made of.
So we put our messy, mixed-up signal into this mathematical prism, and out pop three pure, distinct components. And the key is that these components are totally independent of each other. They're orthogonal, kind of like length, width, and height. Each one tells us something completely unique about the signal's behavior.
And what's really cool is this slide shows two of those fundamental colors. On the left, you've got the gradient component. The easiest way to think about this is flow that starts at a source, at a high point, and just flows downhill. On the right, you have the curl component. This is flow that circulates in loops, like water in a whirlpool, or, you guessed it, value in an arbitrage loop.
And right there, that is our big clue for detection. See, in a healthy, normal system, we expect the signal to only show up in certain components. A fair currency market shouldn't have any of those free money arbitrage loops, so its signal should have zero energy in that curl component. If we suddenly see energy showing up where it's not supposed to be, well, that's a huge red flag.
Okay, so we have our clue. And this brings us to the star of the show, a detector that is specifically designed to spot exactly this kind of signal leakage, when energy spills from one of these poor components into another where it just doesn't belong.
At its heart, the detector is just making a simple choice between two possibilities. Hypothesis 0, H0, is the all clear. The signal's energy is right where we expect it to be. Everything's normal.
Hypothesis 1, H1, is the alarm bell. The signal has leaked into a forbidden area, and that tells us there's an anomaly.
So how does it decide? Well, it's actually a pretty simple but powerful energy detector. It mathematically measures the amount of signal energy that is spilled over into that forbidden zone. If that energy level crosses a certain line that we've set, bing, the alarm goes off. Anomaly detected. It's principled, it's mathematical, and as we're about to see, it's incredibly effective.
Okay, so the theory sounds really elegant, right? But the million-dollar question is, does this new topological detector actually do any better than the old methods that just look at simple graphs, especially when you throw messy, real-world data at it?
The results are, well, they're pretty staggering. This table shows performance using a metric called AUC. Just know that 1.0 is a perfect score, and 0.5 means you're just guessing. Now look at this. Across all these different data sets, currency markets, music listening, football passes, the new topological detector, DSD, gets near-perfect scores. The old graph-based method, it's barely better than flipping a coin.
And this chart tells an even more powerful story. The yellow line shows the performance when you only use the simple connections. But that red line, that's what happens when you include information from the nodes and the triangles, the full topological structure. Look at that massive boost in detection power. It shows that these higher-order shapes aren't just a neat idea. They contain absolutely crucial information.
So let's tie all this together. The takeaway here is really clear. By expanding our lens from simple graphs to the richer world of topology, we get a much, much deeper understanding of complex systems. It gives us the framework to see group interactions, the tools to analyze them, and a powerful new way to find subtle problems we would have totally missed otherwise.
And that really leaves us with a huge question to think about. This whole approach opens up brand new possibilities for research in fields from finance and biology all the way to neuroscience. It forces us all to ask, what hidden shapes might be lurking in our own data, just waiting to be found? Thanks for joining us for this explainer. Hopefully you now have a new lens for seeing the hidden shapes in complex data. The only question now is, what are you going to find when you start looking?